Hi everybody. Today's video is on section 7.2, Trigonometric Integrals. Now, these are going to be integrals that involve very heavy use of trigs and trig functions and powers of trig functions. So here are some integrals integrals we should know, first of all. I'm going to write some integrals we should know, and then I'm also going to write some trig identities that we should all know going into this section. So of course, we need to know all of our trig integrals, so let me write them down as a reminder here. We all need to remember this. I'm not going to put the plus c on these, okay? But, they're all there, of course. We know that this is true. 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 And then we also know that this last one Okay, so these are the 6 basic trig integrals. However, there are a few more that we should know. This one, I don't recommend memorizing it, but I am going to put it here anyway, just because I know for some of you, you might already have this memorized. So this one is going to be, you can also memorize this as the natural log of secant. It's the same thing. Okay, and then we also have the following two. These next two are going to look new, okay, because I don't think that you have used these before. But we have the integral of secant x dx is going to equal the natural log of secant x plus tan x. This is a brand new one, so I'll put a little star here. That one's new. And then it's got a counterpart here. If you want to integrate cosecant x, the answer is the natural log of cosecant x minus cotangent x. Okay. So where do those integrals come from? It is a little bit complicated to derive these. So I think if I do this, it'll be later in the class. And later in this chapter, I will show you where these two formulas come from, okay? But for now, it is definitely worth memorizing them, okay? Put a little time in and memorize these two formulas. It'll make your life easier, okay? Especially the secant one. We see that one more often. So in fact, I'm even going to put an extra little star for that one. Okay, now what about identities, trig identities? So there are trig identities that we need to know going into this section. So let me write those down here. So trig identities we should know. Okay, so first, the most important identity by far are the two Pythagorean identities, okay? So what are the Pythagorean identities? The first one is sine squared x plus cosine squared x is equal to 1. Extremely important. We're going to be using this all the time in this section, okay? So we've got this one, and then if we were to divide all of these terms by cosine squared, we get another identity, another version of this, which is tangent squared x plus 1 is equal to secant squared x. Okay, so these are called the Pythagorean identities. Okay. And by the way, these identities are going to be useful for the next section in the class as well. Okay, so it's not just this one. Next, we have the half angle formulas from Trig. Let me remind you guys of those. So the first one is sine squared x is equal to 1 minus cosine of 2x all over 2. And the other one is cosine squared x is equal to 1 plus cosine of 2x all over 2. Okay. Now, one more thing I want to say here that usually I will write it this way, just because it makes the integral easier to do when you don't write it as a fraction. But you can write it either way, right? These mean the same thing. Okay, so these are called the half angle formulas, okay? So let me just write half angle identities. Right, it's important to understand what's happening here, right? The reason they call these the half angles is that you're going from x to 2x over there. So in other words, you end up doubling your angle or cutting it in half depending on which direction you're using this identity. Okay. Also note that the power went down, so these are also called the power reduction formulas. Okay, so also called power reduction. Okay, so what is the goal in this section? The goal in this section is to integrate products of powers of trig functions. Okay, what I mean is you take powers of trig functions and then you multiply them together, and then you end up solving that integral. Okay, that is the point of this section. So we learn two types in this section, okay? So the first type, type 1, is going to be to solve the following integral. We're going to integrate a power of sine times a power of cosine. So we're going to learn how to do integrals that look like this. Okay? Now, the idea here, okay, what I'm gonna do is I'm going to work through a problem as we learn this method in order to be able to kind of put what we're learning into practice so that you guys understand the different steps here. Okay, so let's start with, so I'm gonna write down a problem here. My problem is gonna be, this will be my example 1. And this problem is going to be the integral of sine squared x times cosine cubed x dx. Okay, so as it stands right now, we have no idea how to do this problem. Okay, there's no way to do it based on what we know so far. Okay, so I'm going to write down the steps for what to do here. The first thing we're going to do is we're going to peel off a cosine. Why am I going to do that? So what does it look like if I peel a cosine off? It looks like this. Hope you guys see what I did there. I peeled a cosine off. Why did I peel a cosine off? I peeled a cosine off because the power of cosine was an odd number. We still don't understand, how this is helpful, but that's coming, I promise, okay? But let me write down the steps as I go, okay? Step 1. Whichever one is odd, you peel that off. So let me just say if m is odd, peel off 1 sine x. Okay? Yeah. We're going to do, so I want to write out the steps here, okay? So if m is odd, you peel off 1 sine x. Now let me go back to this problem, okay? What do I do next? Here's the idea, guys. We know that if we were to let u, let's say we wanted to do a u substitution. If we were to let u equal sine of x, then the du is going to be cosine x dx, right? So here's the idea. If we peel off a cosine, that means that we can turn these guys into sine, because isn't it true that sine squared x plus cosine squared x is equal to 1? But this means that cosine squared x is equal to 1 minus sine squared x. So that means I can take this guy and rewrite it there. Okay. So this gives me what? Sine squared x times 1 minus sine squared x, and then cosine x dx. Okay. So what happens if sine had been odd? We would have done the same thing in reverse, okay? So let's write this down before, okay? So if m is odd, then you peel off of a sine x, okay? And then step 2 is use the Pythagorean identity sine squared x is equal to 1 minus cosine squared x to convert all other sines to cosines. Okay. Step 3, let u equal cosine x. And then du is negative sine x dx, right? And integrate. Okay, these are the steps. Now, let's go ahead and do the rest here. The point is here, we're going to let u equal sine x. Why are we letting u equal sine x? Because in this problem, the number of cosines is odd. So let me just write that down here as my first little star. If n is odd, do the same process with sines and cosines flipped. Okay. Another double star, if both are odd, do the above with the smaller odd. Okay. And finally, the third one, or actually, let me, this is a lot, so let me explain what I did here. The first star that I wrote, if n is odd, do the same process with sines and cosines flipped. The point is that what we're doing works regardless of which one is odd, but you just have to treat the sines and cosines accordingly. So, if you have an odd number of a particular sine or cosine, you peel one of those off, and then you use the Pythagorean identity to convert all of the rest to the other function. Okay, so what we have here is always what's going to happen, which is you're going to have all of one function. We have all sines except for the cosine, and then we let u equal sine x. Now the du is equal to cosine x dx, which is right here because you peeled it off in advance. So what's nice about this is we then end up getting an integral that we can solve. Okay, so now we just solve it. U squared minus u to the fourth du. And then let's actually take the antiderivative. We get 1/3 u cubed minus 1/5 u to the fifth plus c. So far, that's our answer if we were to leave it with u's, but we can't. So we need to convert those back to sines. So u is sine x, right? So this would be sine cubed x minus 1/5 sine to the fifth x plus c. Okay. So going back, again, I hope that this process makes sense, right? If you have an odd number of something, then that means after you peel one off, you're going to have an even number of something. And then, with those even number of things, the Pythagorean identity allows you to convert it to the other trig function, right? And so now if you have only sines and a single cosine, or only cosines and a single sine, a u substitution will always work. Okay? So I'm hoping that explanation makes sense, and I'm going to be doing a lot more examples so that you guys can see all the different possibilities. Okay? So let's go ahead and do another problem. Okay, so number 2. We're going to do the integral of sine cubed theta times cosine to the fourth theta d theta. Okay, so let's follow the steps from before as closely as we can. So the first step, remember, is to peel off one of the odd powers, right? In this case, sine is odd, right? Sine is odd. So we're going to peel off a sine, and so this is how we're going to write it, okay? Sine squared theta, cosine to the fourth theta, and then I've peeled off a sine, so there it is, sine theta d theta. Next, we need to convert all the sines to cosines using the identity, right? So remember, sine squared theta is equal to 1 minus cosine squared theta. So that means I could take this and replace this with that, right? And so I get the integral of 1 minus cosine squared theta times cosine to the fourth theta times sine theta d theta. Now, you might wonder, do I just multiply the cosine through now? I would say no, right? Because that's more writing than necessary. I think it's better to use your u substitution now. So we're going to let u equal, in this case, cosine theta, right? Because we want the du to be this part right here. Okay. Remember, du in this case is going to be negative sine theta d theta. So we do have to worry about that extra negative sign. Let's not forget about it. So we end up with a negative. And then we have 1 minus u squared times u to the fourth, and then du. What is this going to equal? I'm going to multiply that u to the fourth through and also multiply the negative through. So this ends up giving me u to the sixth minus u to the fourth du. So this is what we get. Now what? Well, now we can just solve it, right? So this is going to equal 1/7 u to the 7th minus 1/5 u to the 5th plus c. And from here, you let u equal cosine theta, and so you end up with 1/7 cosine to the 7th theta minus 1/5 cosine to the 5th theta plus c. And so this is our final answer. Let me make that a little more clear. There we go. Okay. Again, it's a pretty straightforward process, right? Let me do another example. Okay, so this will be number 3. I'm going to illustrate what you do when you have two different ones that are odd. Okay, so we notice that both are odd, but I said to go with the smaller odd, right? So where would the smaller odd be? The smaller odd, of course, is the cosine. So you're going to see why in a second we go with the smaller one. It's because using the Pythagorean identity is it's easier when you have a smaller number of evens, okay? So let's see what happens. So we're going to peel off a cosine, right? So we end up with sine 7th theta, cosine to the 4th theta times cosine theta d theta. Now, we've never seen one like this before where we actually have 4 cosines now. We don't have 2 cosines. So we're actually going to need to use the Pythagorean identity, but a little bit modified. Okay? So remember, we want to turn everything else into a sine. So we know that cosine squared theta is 1 minus sine squared theta, right? So that means that cosine to the 4th theta, you'd have to square both sides, wouldn't you? So we're going to need to square the Pythagorean identity. So this is what we get. I know that seems like the algebra is going to get nasty, but it's really not that bad because at this point we can just do the u substitution right away. So we're going to let u equal, remember we want the du to be that, so we're going to let u equal sine theta, and then the du is cosine theta d theta. So what do we end up with here? We get u to the 7th, and then 1 minus u squared, and then du. Now what? Well, you have to do the algebra now, but it's really not that hard, right? We want to square that first. So how do you square 1 minus u squared, right? It's going to be 1 minus 2u squared plus u to the 4th, and then du. So all I did was I squared that second part, and now I'm going to distribute the u to the 7th, right? I just want to use the distributive property. And so this is going to equal the integral of u to the 7th. Remember to add exponents here, minus 2u to the 9th, and then plus u to the 11th du. Okay, now we can finally take the antiderivative, right? So we do the power rule. We get 1/8 u to the 8th minus, remember that's going to be to the 10th, so it's going to be 2 over 10, so that's 1 over 5, u to the 10th, plus 1/12 u to the 12th plus c. But remember, u is equal to sine theta, so let's go ahead and convert back. And I'm going to write not just sine, but I'm also going to write it in alternating order. I'm going to write it with the biggest power first, just because it's usually good practice to do that. So I have 1/12 sine to the 12th theta. Oh, let me write that a little neater. Sine to the 12th theta minus 1/5 sine to the 10th theta plus 1/8 sine to the 8th theta plus c. Okay. So there you go. Now, a question some of you may have is, what happens when none of them are odd? And this is a good question, okay? So let me just say tip. If neither is odd, you have to actually do a lot more work. So I'm going to say try using half angle identities. Until an odd power is obtained. Okay, what I mean by that is, if you cut an even number in half enough times, it will become an odd number. Okay, so that's true for any even number. However, this could take a lot of steps, so I don't want to minimize that these problems can get quite challenging when you have a large number of evens. Well, I do want to do a couple of examples just to illustrate how that works. Let's start with, so our next one is going to be number 4. This one's not going to be too bad. We're going to start with one that's not that hard. I'm going to do sine squared x dx. Okay. So remember what I said earlier, right? If you have an even, you can use half angle. Let's go ahead and look at the half angle formula just to remind us of what it is, right? So our half angle formula is, for sine squared, it's 1/2 minus 1/2 cosine of 2x, right? So let's go ahead and use that right away. Now, the good news is when you write sine squared in this way, you can actually integrate it right away. So what do you get? So we get 1/2 x, right? And how do you integrate 1/2 cosine 2x? Remember our linear substitution shortcut that we learned about in the integration review video, right? You could do a u sub here for 2x, or you could just do it in your head. And so you end up with, remember, you divide by the slope, we get 1/4, and then the integral of cosine is sine 2x. Okay, and then plus c. And that's actually our full answer. Okay, there's no reason to, this was nice, right? We didn't actually need to even use a u substitution to do this one. For my next problem, though, it's going to be a lot more challenging. So I want to show you guys number 5. we're going to do the integral of sine squared t cosine squared t dt. This is tricky because we have two of them and they're both even. So the trick here is going to be to use half angle on each one. So we're going to use half angle for that one, but then we're also going to use it for that one. So let me write it in this form, right? This is going to be 1 minus cosine of 2t divided by 2 times, the other one is 1 plus a cosine of 2t divided by 2 dt. So what do we get when we multiply these two together? I could pull 2 times 2 is, well, yeah, let me write it this way. If I multiply the numerators together, 1 minus cosine of 2t times 1 plus cosine of 2t, what is that equal to? Remember, I'm using this. I know that a minus b times a plus b is equal to a squared minus b squared. That's the difference of squares formula. So I know the top is going to be 1 minus cosine squared of 2t. And then the bottom is 4, right? But I can write it this way. Okay. Now what? So I can integrate one of these pieces, right? But I want you guys to take a good look at cosine squared 2t, right? I have a square there, so I have no choice but to use the half angle again. So I'm actually going to use half angle on this guy again. Now there's a catch though. I don't have cosine squared t, but I have cosine squared 2t, which means you're actually going to double everything in the problem, right? So what is cosine squared 2t? You actually get 1/2 plus 1/2 cosine of, instead of 2t, it's going to be 4t. And just to clarify what I'm doing really well, if we come back over to our half angle formula, what I'm saying is if you were to put a 2x in here instead of an x, then that means that you're going to get a 2x instead of an x here. In other words, it's going to be a 4x altogether, right? So that's what we're doing here. We are doubling the input, and so then the output gets doubled also. Okay? So let's write out what we get here. So this is my dt. So here's what we get. We end up with the integral of 1/4, and then I have a minus an eighth, and then I have minus 1/8 cosine of 4t dt. The good news is our power is now 1, so we can keep going. What's 1/4 minus 1/8? So if I combine these two, 1/4 minus an eighth is an eighth. Okay, so 2/8 minus 1/8, right? And so if I were to write out what I get 1/8 minus 1/8 cosine of 4t. Now I'm actually ready to do the antiderivative here. Okay, so what do I get here? I can integrate that, so this is equal to 1/8 t. And then remember to use my linear substitution trick. I'm going to divide by the slope. The slope is 4, so I know I'm going to divide by 4, so I get minus 1/32. And then that becomes a sine of 4t, and then I have plus c. Okay? So that should be the answer. Okay, again, it's not easy, but when you have only even powers, you can get away with just using half angles there. So now that we've seen a lot of examples of how the sine and the cosine trick works, we're going to look at a different type now. So our type 2 is going to be on what happens if we have secants and tangents. Secants and tangents. Okay. This is going to be a little more complicated. It's not as simple as sines and cosines where you just peel off a sine or peel off a cosine. And the reason it's not as simple is because the derivative of secant and tangent are more complicated than just giving you a single trig function, right? So there are going to be two cases. First, if n is even. This is going to be our first case, but also not just n being even, we also need for n to be at least 2. So let me say, let me write it this way actually. If n is even and n is bigger than 2. I have to say this because if n is 0, that's still considered an even number. However, this trick will not work. So if n is even and n is greater than or equal to 2, these are the steps. Step 1 is you're going to peel off a secant squared x. Okay? Peel off secant squared x. And step 2, you're going to do what you did before, which is change all of the secants over to tangent. So use the Pythagorean identity secant squared x is equal to tan squared x plus 1. You're going to use that to convert all other secants to tangents. Okay. And then step 3, let u equal tan x. Why does this work? Because the derivative of tan x is secant square x, right? So that's going to allow you to get rid of that secant square that you peeled off. You need it to be even because after you take 2 of them off, you need to still have an even number of them left so that you can convert them to the other function, to tangent. Okay. So this is the method if n is even. So on the next page, I want to do the method behind the other function, right? So this is letting u equal tangent. So what happens if you want to let u equal secant? So let me go over the condition for that one. If, for this condition, you need m to be odd and at least 1 n. So if m is odd and you have at least 1 n, what you can do in this case are the following steps. So step 1 is you can peel off a secant x and a tan x. Okay, so peel off secant x, tan x. And remember, you're going to want to let u equal secant now, so that means that you need to convert the tangents, convert the rest of the tangents to secants. So step 2, use the Pythagorean identity tan squared x equals secant squared x minus 1, right? So use that Pythagorean identity to convert the other tangents to secants. And then step 3, let u equal secant of x, and that means that du is going to be secant x tan x. Okay, I guess I should say also is to, of course, integrate. That goes without saying, but I should write that down as part of that, okay? Now, hopefully you guys understand, right? If you have an odd number of tangents, then you can peel off one tangent and one secant. That's why you need at least one secant to make this work also. And now the number of tangents is even, right? If it was an odd number and you took one away, now it's an even number. And so you should be able to use the Pythagorean identity to convert tangents to secants. Okay, so I should also say one last thing here. So if m is even and n is odd, this would be the case where, you can't use any of these. I want to just say, try other techniques and experiment. I know that I'm being vague here. That is because these are very hard problems if m is even and n is odd, okay? Because you're not able to use any of these techniques. And so I am going to do an example like that just to show you what I would do, okay? Okay, so let's see. What number are we on here? I want to do the next example, so number 6. Let's go ahead and try one. We're going to do the integral of tangent cubed x secant x dx. So remember, we need an even number of secants or an odd number of tangents. And we notice that this guy is odd. Okay, so this is going to be the method that we take. So what do we do when the number of tangents is odd? Remember, we just said in the steps you're going to peel off a secant and a tangent. So this is going to equal, peel off a secant and a tangent. So we're left with 2 tangents here, right? And then I have a secant x tan x dx, right? Now we're going to use the Pythagorean identity, right? We know that tan squared x is equal to secant squared x minus 1. So this is going to replace this, right? We know we need to convert it to secants. So this is equal to the integral of secant squared x minus 1 times secant x tan x dx. And now we finish our plan here. We're going to let u equal secant x. So then du is equal to secant x tan x dx, which is exactly right here. And again, that's why we peeled it off, right? We peeled it off so we could save it for this part. Okay. So what do we get now after you let u equal that? You get u squared minus 1 du. And we can go ahead and take the antiderivative of that. We get 1/3 u cubed minus u plus c. And so this is equal to 1/3 times secant cubed x minus secant x plus c. There you go, right? Wasn't too bad. Let's go ahead and try another one. This is going to be number 7. We're going to do the integral of tangent to the 4th x secant to the 6th x dx. Bigger numbers, right? So remember what we needed. We needed the number of tangents to be odd or the number of secants to be even. And we notice right here that that is even, okay? So this is why we can use this method. So remember the strategy. We need to peel off a secant squared. So if you peel off a secant squared, you get tan to the 4th x. We have 4 of them left, secant to the 4th x, and then I'm going to write secant squared x dx, okay? Now, remember, we need to turn everything else now into a tangent using the identity, right? So we know that secant squared x is equal to tan squared x plus 1. So that means that secant to the 4th x, I have to square this side. Okay. So that, what I have here is what I can replace this with. So I have the integral of tan to the 4th x times tan squared x plus 1 squared, and then I have a secant squared x dx. So next, we know that we should let u equal tangent of x. So if we let u equal tangent of x, du is going to be secant squared x dx. Again, we already peeled that off so that we have it ready to go. And so this now becomes u to the 4th times u squared plus 1 squared du. So do the algebra like in that other example. We're going to first, using exponents, we're going to square this. We get u to the 4th plus 2u squared plus 1, and then du. And then we distribute that. Distribute u to the 4th. Again, you're going to add exponents here, right? So when you distribute that, you end up with u to the 8th plus 2u to the 6th plus u to the 4th, and then du. Okay, so now integrate that. You get 1/9 u to the 9th plus 2/7 u to the 7th plus 1/5 u to the 5th plus c. And finally, you replace u back with tangent. So this is equal to 1/9 tangent to the 9th x plus 2/7 tangent to the 7th x plus 1/5 tangent to the 5th x, and then plus c. Okay. Again, having the right sign of odd or even, it still gets more algebraically complicated the bigger the number is. But the method that I tell you will always work if you satisfy those two conditions. For my last example, I'm going to be doing one that seems like it's going to be easy, but it is a lot more difficult than we believe, okay? It's going to be secant cubed x dx. Now, again, we cannot use any of the previous methods that we know because we need an even number of secants to be able to use the secant trick, okay? So we cannot just peel 2 off. So here's what we're going to do. I'm actually going to do this using, now there's a lot of things we could try here, but I want to try using integration by parts. This is what we learned in the previous section, right? In section 7.1. So what am I going to use for my u and my dv? I'm actually going to let u equal secant x and dv be secant squared x dx, right? Because I actually know how to integrate that. So then, what do I get for my du? And what do I get for my v? My du is going to be the derivative of secant x. It's secant x tan x. And my v is going to be the antiderivative of secant squared, which is tan x. Remember, I took a derivative here, right? The derivative. And here I took the integral. Okay? So remember the integration by parts formula. The integration by parts formula, so if I were to call this guy I get that I is equal to u times v, so that's secant x tan x, minus the integral of v times du. So that's going to be secant x times tan squared x dx. Okay, I just multiplied v times du. It doesn't really look like we've gotten to a better place here, right? But I do want to point something out. Since we started off with secant cubed, what we ended up with kind of looks along the same lines, doesn't it? In fact, isn't tan squared x the same as secant squared x minus 1 using our Pythagorean identity? So let's see what happens if we actually plug that in, right? We end up with the following. I equals secant x tan x minus the integral of secant x times secant squared x minus 1 dx. But if I were to simplify that guy algebraically, I get the following. Secant cubed x, and I'm going to split this up into two integrals here. This one's going to be plus the integral of secant x dx. Okay. So this is what I have. Now understand that this guy is actually the same integral that I started with, right? This guy is I. What about the one on the right? We can actually solve that one. So here's what we end up with then. We get I equals secant x tan x minus I plus, and then remember, this is one of the ones I said to memorize. The integral of secant is natural log of secant x plus tan x. Okay. So remember the trick from integration by parts. We can actually take this guy, we can add I to both sides of this, and we could solve for I algebraically. So if we do that on the next page, we get 2I equals secant x tan x, and then I think we had plus the natural log of secant x plus tan x. Okay, and so divide everything by 2. We end up with I equals 1/2 secant x tan x plus 1/2 the natural log of secant x plus tan x, and then plus c. And so we've got our answer there. You are not going to see problems like this often in this class. They do show up sometimes on the homework, but remember, the main thing here is to learn the main methods, right? Our main methods here are exactly when secant is even or tangent is odd, or when sine and cosine are both odd. Those are the main things, and then the others, when you do see problems like that, you just need to try some experimentation. And don't forget, we have these other techniques that we keep learning, like integration by parts and so on. Okay, guys, that's it for this video. Thank you so much for watching. Hope it was helpful.